In this video, I will introduce a way of performing mathematical operations in linear algebra called Falk's scheme. Falk's scheme simplifies the complicated process of multiplying matrices and generalizes to all basic tensor operations. It is based on a paper published by Falk in 1951 in the German journal Zeitschrift für angewandte Mathematik und Mechanik entitled A Clearly Laid Out Scheme for Matrix Multiplication. That's my rough English translation of his title. I am not aiming for any deep insights in this video. My goal is to simply lay out the mechanics of Falk's scheme and show you how it makes various operations in linear algebra much easier. Let's say you want to multiply two matrices M and P and their products result in a new matrix Q. Falk's scheme exploits the understanding that if you want to find a particular element of Q, say Q23, Q23 is found by taking the inner product of the second row of M with the third column of P, like so. Falk's scheme makes this inner product process easier to visualize, and let's do it with some numbers to make it more concrete. In Falk's scheme, the target matrix Q is placed in the center, then place the first matrix in the product M on the left of the target matrix, then place the second matrix in the product P above the target like so. Now, each element of the target matrix Q can be calculated by performing a series of inner products of rows of M and columns of P, where the target element in Q is aligned with the row of M on the left and the column of P above. Q11 is equal to 1 times negative 1 plus 2 times 1 plus negative 1 times 1, which all sums to 0. Q12 is equal to 1 times 2 plus 2 times 1 plus negative 1 times 0, which sums to 4. Q13 is equal to 1 times 5 plus 2 times 4 plus negative 1 times negative 3, which sums to 16. And we can keep on going, finding each element of Q by taking an inner product of the row of M and the column of P that align with the location of the element in the target matrix Q. Now, we could end here, but Falk's scheme is so much more powerful than just helping us to multiply square matrices. First, Falk's scheme is great for multiplying non-square matrices. For example, what if we needed to multiply a 2 by 3 matrix and a 3 by 2 matrix? We follow the same procedure. Put M on the left and P above. Now here's the first useful thing. The number of rows in the target will always be the same as the number of rows in M, and the number of columns in the target will always be the same as the number of columns in P. Thus, Falk's scheme tells us that the result of multiplying a 2 by 3 matrix and a 3 by 2 matrix will be a 2 by 2 matrix. Now we follow the same procedure as before, filling out the elements of each cell of the target by taking inner products of rows of M and columns of P. Q11 is 1 times 4 plus 0 times 1 plus negative 1 times 3, which sums to 1. Q12 is 1 times 2 plus 0 times 1 plus 1 times 0, which sums to 2. And we can keep on going to fill out the lower two cells of Q in a similar way. Another feature of Falk's scheme is that it makes it obvious what mathematical operations in linear algebra are not allowed. For example, let's try to multiply a 2 by 3 matrix and a 4 by 3 matrix. Let's just go ahead and try to do it. We arrange the matrices to the left and above as before. Falk's scheme tells us the resulting Q should be a 2 by 3 matrix, but when we try to compute Q11, we run into a problem because the first row of M has 3 elements, but the first column of P has 4 elements. There is a lonely entry in P with no friend in M to multiply with. This reveals that this multiplication is impossible. The number of elements in each row of M must match the number of elements in each column of P. But there's even more you can do with Falk's scheme. You can compute the action of a matrix M on a column vector V like this. Put the matrix on the left, the column vector above, and you can see that the target must be an object that is 1 column wide and 3 rows deep, namely a column vector with the same number of rows as the matrix M. Again, each entry in the target column vector is an inner product of a row of M and the column vector. The first entry of V prime is 1 times 1 plus 2 times 1 plus negative 1 times negative 1, which gives us a grand total of 4. The other two entries are computed in a similar fashion, like so. Falk's scheme works for inner products, which is understood as the product of a row vector and a column vector. Using Falk's scheme, you see immediately that the target must be a 1 by 1 matrix, also known as a scalar, and the procedure is just as before: 1 times 3 plus 1 times 2 plus -1 times 1 for a grand total of 4. Falk's scheme also shows you why a matrix M can only operate leftward on a row vector, but not rightwards. Let's start by operating M rightwards on a row vector. Following the rules of Falk's scheme, you would predict that the resulting M times V is a 3 by 3 matrix, but when you try to perform the multiplication, you can't do it because the first row of M has 3 elements, but the first column of V has only 1 element. The multiplication is disallowed. If, on the other hand, you arrange V on the left and M on the right, Falk's scheme predicts a 1 by 3 row vector as the target, and this multiplication is legitimate because the row vector V has the same number of entries as the column of M. The entries of the resulting row vector can be calculated in the usual way. The final superpower of Falk's scheme is that it works for outer products. Suppose you want to take the outer product of a column vector U and a row vector W. Let's just follow the rules of Falk's scheme. The column vector goes on the left, the row vector goes above, and the result is, as you know if you understand outer products, a 3 by 3 matrix. We now take the inner product of each row of the column vector and each column of the row vector. Since there is only one entry, there is no need to sum anything. Therefore, Q11 is 3 times 1, which is 3. Q12 is 3 times 1, which is 3. And Q13 is 3 times -1, which is -3. We keep going like this until the rest of the entries of the 3 by 3 matrix are filled. And that is Falk's scheme. It is surprisingly versatile and really helps to alleviate some of the intellectual effort of trying to understand how different kinds of multiplication operations work in linear algebra. I hope you found this video useful in your linear algebra journey.